When you look at a solid object, perhaps the table in front of you, the screen you are reading this on, or even your own hand, it feels continuous, dense, and tangibly real. But if you were to zoom in, past the cells, past the complex molecules, down to the realm of individual atoms, you would encounter a startling geographical reality. The building blocks of our world are almost entirely made of nothing. If you imagined the nucleus of an atom scaled up to the size of a marble sitting on the 50-yard line of a massive sports stadium, the electrons orbiting it would be like tiny pinheads buzzing around the very highest rows of the stadium seats. Everything else in that vast arena, the immense expanse separating the core from its outer boundary, appears to be an absolute, unblemished void. For generations, we were taught that this micro-universe is a quiet, dead expanse of nothingness. But modern physics has pulled back the curtain on this illusion, revealing that the space between atoms is not empty at all. In fact, it is a roiling, dynamic ocean of activity, governed by forces and structures that construct the very fabric of our physical existence. If you enjoy peeling back the layers of our universe to see the astonishing mechanisms operating just out of sight, taking a brief moment to like this video and subscribe to the channel makes an immense difference in helping these deep scientific explorations reach more minds. Now let's journey into the true nature of the void. To comprehend how empty space can be full, we must first look at how our understanding of nothingness was forged over centuries of intellectual conflict. For thousands of years, the brightest minds argued that a true vacuum could not exist in nature. The great philosopher Aristotle put forward a doctrine that governed Western science for 2 millennia, the idea that nature abhors a vacuum. Aristotle reasoned that if a region of space were genuinely devoid of all matter, there would be no resistance to block an object's path. Consequently, any object moving through a perfect void would travel at an infinite speed, a concept he deemed completely logical but physically absurd. To Aristotle and his followers, space was a plenum, a universe packed tightly from edge to edge with physical substances, whether it was the air we breathe, the water in the oceans, or the mysterious ether filling the celestial heavens. Space, by definition, had to be occupied by something. This philosophical certainty stood unchallenged until the mid-17th century, when a series of brilliant experimentalists decided to test the limits of nature's alleged abhorrence. In 1643, the Italian physicist Evangelista Torricelli filled a long glass tube with heavy, liquid mercury, sealed one end, and inverted it into an open dish. Instead of rushing out entirely, the mercury trapped inside the tube dropped down to a height of roughly 30 inches, leaving a mysterious clear pocket at the very top. Torricelli had inadvertently created the world's first artificial vacuum. He recognized that it was not nature's mystical terror keeping the mercury suspended, but rather the literal physical weight of Earth's atmosphere pushing down on the liquid in the open dish. The space at the top of the tube was, for all intents and purposes, cleared of air. We live submerged at the bottom of an ocean of the element air, which by unquestioned experience is known to have weight. Torricelli wrote, fundamentally shifting how humanity viewed the atmosphere. The scientific community was deeply shaken by this revelation, and the debate over what truly occupied that clear space at the top of the tube intensified. Seeking definitive proof, the French mathematician and philosopher Blaise Pascal sent his brother-in-law up the slopes of the Puy de Dôme mountain in 1648 with a mercury tube in hand. As the climbing party ascended into the thinner mountain air, the column of mercury dropped lower and lower. This elegant experiment confirmed that the weight of the air changed with altitude, proving that the atmosphere was a finite blanket wrapping the planet, and that the space above Torricelli's mercury was indeed a vacancy of air. Not long after, in the 1650s, a German physicist and mayor named Otto von Guericke designed a mechanical air pump that turned this abstract physics debate into a public spectacle. He constructed 2 massive copper hemispheres that fit together cleanly, pumped the air out from the hollow space within them, and challenged teams of powerful horses to pull them apart. The horses strained in vain against the invisible weight of the surrounding atmosphere, which slammed the halves together because there was no internal air pressure to counteract it. Shortly thereafter, Robert Boyle refined these air pumps in England to study the behavioral mechanics of this manufactured nothingness. He placed a ticking watch inside a sealed glass chamber and slowly evacuated the air. As the internal environment thinned, the sound of the ticking diminished until it vanished altogether. This proved a vital physical law. Sound is a mechanical wave, a structural compression that requires a physical medium like air molecules to travel. When you remove the matter, the sound dies. Yet Boyle noticed something else. Even when the chamber was completely silent and emptied of its air, light passed through it with perfect ease. You could still see the watch perfectly clearly. This simple observation planted a profound seed of doubt in the minds of physicists. If the matter was gone, what was carrying the light? The answer began to crystallize in the 19th century through the extraordinary visual intuition of Michael Faraday. Lacking formal mathematical training, but possessing a genius for physical visualization, Faraday spent years experimenting with electricity and magnets. He was deeply troubled by the prevailing Newtonian concept of action at a distance, the idea that a magnet could somehow reach across a completely empty void to pull on a piece of iron without any physical intermediary. To resolve this logical knot, Faraday proposed that the space surrounding a magnet is not empty. It is populated by an invisible web of influence that he called a field. When you scatter iron filings around a magnet, they do not align randomly. They trace out elegant, sweeping curves that map the contours of this hidden architecture. The magnet alters the very space around it, and any object entering that space is simply responding to the local environment. In the 1860s, the Scottish physicist James Clerk Maxwell translated Faraday's visual insights into a set of elegant mathematical equations. Maxwell discovered that electric and magnetic fields are deeply intertwined, and that changes in one field trigger changes in the other. He calculated that these shifting disturbances could ripple through space as self-sustaining electromagnetic waves. When Maxwell computed the speed at which these ripples would travel, the math yielded a striking number, approximately 300,000 kilometers per second. This was precisely the known speed of light. Maxwell had discovered that light is not an independent particle flying through empty space. It is a wave propagating through the electromagnetic field. This realization radically alters how we view the vast spaces between stars, and more importantly, the tiny spaces between atoms. When light travels from a star billions of light years away, or when an electron interacts with a nucleus inside an atom, they are operating within this pervasive electromagnetic field. The field does not vanish when you remove the atoms. It is an intrinsic property of space itself. In 1915, Albert Einstein expanded this field concept to gravity with his general theory of relativity, demonstrating that space-time itself is a geometric field that curves and flexes in the presence of mass and energy. By the dawn of the 20th century, physics had established that what we call empty space is continuously saturated by at least two fundamental cosmic fields, electromagnetism and gravity. Yet classical physics still assumed that if you went to a region of space far away from any stars, charges, or gravitational bodies, these fields could be brought to a state of absolute rest. In the classical mindset, a field could have a value of exactly zero, smooth, flat, and perfectly calm, like a mirror-like lake on a windless morning. But this comforting picture of a tranquil void was thoroughly shattered by the arrival of quantum mechanics. The quantum revolution began when physicists like Max Planck and Albert Einstein realized that energy is not continuous, but comes in discrete packets called quanta. As the mathematical framework of quantum mechanics was formalized in the late 1920s, Werner Heisenberg introduced his famous uncertainty principle. This fundamental law states that there are certain pairs of physical properties that can never be precisely known at the same time. While it is often discussed in terms of a particle's position and momentum, the uncertainty principle applies just as rigidly to energy and time. The law dictates that you cannot measure the exact energy of a system within an infinitely precise slice of time. The shorter the time interval you look at, the larger the uncertainty in the energy becomes. This has a profound and unsettling consequence for the fields filling the empty space between atoms. If a quantum field were to become completely still, having an energy value of exactly zero, it would mean we knew both its precise value and its rate of change simultaneously. The laws of quantum mechanics strictly forbid this absolute precision. Consequently, a quantum field can never be truly zero. It must possess an irreducible, fundamental fuzziness. Even if you cool a region of space down to absolute zero, removing every single trace of thermal energy, and evacuate every atom of matter, the quantum fields inside that space will continue to twitch and vibrate. This lowest possible energy state of the universe is called the vacuum state, and its energy is decidedly not zero. This persistent baseline activity is known as zero-point energy. The vacuum is not a static stillness. It is a restless, humming medium experiencing continuous, spontaneous quantum fluctuations. This brings us to the profound revelation of modern physics, quantum field theory. This framework completely redefines what matter actually is. In our everyday lives, we conceptualize the universe as a vast empty stage where tiny solid particles, like electrons and quarks, act as the actors, moving around and colliding with one another. Quantum field theory turns this entire perspective inside out. It states that the fundamental ingredients of the cosmos are not particles at all. The fundamental ingredients are the fields themselves. Imagine the universe not as an empty room, but as a space tightly packed with a collection of overlapping, cosmic sheets that span the entirety of existence. There is an electron field stretching across the universe. There is an electromagnetic field, a quark field, a Higgs field, and many others, all coexisting within the exact same space. When one of these fields is quiet, it exists in its vacuum state, humming with baseline zero-point fluctuations. But when energy is injected into a field in a specific way, it creates a localized, stable ripple or excitation. That localized ripple is what our instruments detect as a particle. An electron is not a solid billiard ball rattling around an atom. It is a localized wave, a structural excitation traveling through the universal electron field. A photon is a ripple in the electromagnetic field. A quark is a vibration in the quark field. The particles that make up your body, the air you breathe, and the stars in the night sky are not separate entities occupying empty space. They are simply the visible tips of vast, invisible oceans of fields, doing something dynamic. This means that the vast, seemingly empty arena inside an atom, between its dense nucleus and its distant electrons, is actually a highly active junction where these universal fields intersect and interact. It is an environment vibrating with potential, crowded with the invisible structures that dictate the laws of chemistry and materials science. To make this reality even more striking, we can look to the work of the British physicist Paul Dirac. In 1928, Dirac formulated an equation that successfully united quantum mechanics with Einstein's special theory of relativity to describe the behavior of the electron. The Dirac equation was remarkably successful, naturally predicting properties like electron spin, but it also produced a deep mathematical conundrum. It allowed for solutions where electrons possessed negative energy. In classical physics, a negative energy state is often dismissed as a mathematical artifact, but in the quantum realm, systems naturally cascade down to the lowest accessible energy level. If negative energy states existed, every ordinary electron should instantly drop into them, releasing an infinite burst of radiation, causing all matter to collapse in a fraction of a second. To salvage the stability of the universe, Dirac proposed an incredibly bold hypothesis. He suggested that all of these negative energy states are already completely occupied. According to this model, what we call empty space is actually a completely full, infinite ocean of negative energy electrons. Because this sea is perfectly uniform and fills every point in space, we do not notice it in our day-to-day lives. It acts as the invisible baseline of reality. Furthermore, because of a quantum rule called the Pauli exclusion principle, which states that no two electrons can occupy the exact same quantum state, ordinary positive energy electrons cannot fall into these negative states because there are no vacant spots available. Dirac called this cosmic reservoir the Dirac Sea. Dirac then reasoned that if you were to strike this invisible sea with a sufficiently powerful burst of energy, such as a high-energy photon of light, you could physically knock one of these negative energy electrons out of the sea, elevating it into a normal, positive energy state, where it could be observed as a regular electron. But in doing so, you would leave behind an empty space in the sea, a literal hole in the negative energy vacuum. This absence of a negatively charged electron would behave exactly as if it were a real particle with a positive charge. Dirac had mathematically predicted the existence of antimatter. Just a few years later, in 1932, the physicist Carl Anderson observed this exact signature in cosmic ray experiments, discovering the positron, the antimatter twin of the electron. While the modern mathematical interpretation of quantum field theory has evolved past the literal image of a physical sea of negative particles, the core physical truth remains unchanged. The vacuum state of our universe is an active, vital medium capable of birthing matter and antimatter pairs out of what appears to be nothing. Through the lens of modern physics, empty space is revealed to be a landscape of profound complexity. The immense distances separating the nucleus of an atom from its distant cloud of electrons is not a barren wasteland, but a theater of continuous quantum orchestration. It is a space woven tight with fields, humming with zero-point energy, and pulsing with spontaneous fluctuations. Matter does not merely exist in space, it is born from space. The physical world we touch and see is simply a harmonious vibration playing out across the invisible, eternal oceans that fill the void. This foundational shift from classical particles to universal quantum fields demands a complete reassessment of the atomic landscape. When we look at a single atom of hydrogen, the simplest element in the cosmos, we are taught to picture a lone proton at the center with a single electron tracing a fuzzy orbit around it. But this textbook model completely misses the true majesty of the subatomic domain. The space between that proton and electron is not a dead, passive background. Instead, because fields are the fundamental reality, that atomic interior is a complex, high-stakes arena where the electron field, the electromagnetic field, the quark fields, and the gluon fields are constantly intertwined, communicating, and interacting at rates that defy human comprehension. To understand the density of action occurring within this micro-universe, we must look closer at the concept of quantum fluctuations and how they manifest as what physicists call virtual particles. The Heisenberg uncertainty principle allows the universe to borrow energy from the vacuum, provided that energy is returned within a vanishingly small window of time. The larger the energy borrowed, the shorter the time it can exist before it must disappear. Because mass and energy are two sides of the same coin, as dictated by Einstein's E equals mc squared, this borrowed energy can manifest as physical matter. Within the empty space inside an atom, the universal fields are constantly taking advantage of this quantum loophole. Out of the apparent void, a photon can spontaneously flash into existence. That photon can then rapidly split into an electron and its antimatter twin, a positron. These two particles, born from the vacuum state itself, exist for a fleeting fraction of a second, trace a tiny loop in space, and then collide with one another, annihilating back into a photon before returning their borrowed energy to the underlying field. This process happens everywhere, all the time, at every single point in space. The vacuum between the atomic nucleus and the orbiting electrons is thick with these virtual particle pairs, a chaotic, subatomic foam that is constantly boiling just beneath the surface of measurable reality. You might naturally wonder if these virtual particles are merely a clever mathematical trick a convenient accounting method used by theoretical physicists to make their equations work. Or if they are genuinely real, the answer is found in one of the most precise scientific measurements ever conducted in human history: the Lamb shift. In 1947, an American physicist named Willis Lamb was studying the fine details of the hydrogen atom's energy levels. According to the best relativistic quantum mechanics equation available at the time, the Dirac equation, two specific energy states of the hydrogen electron should have had the exact same energy. They were supposed to be perfectly degenerate. However, when Lamb used precise microwave techniques to probe the hydrogen atom, he discovered a tiny, distinct discrepancy. The two energy levels were slightly shifted relative to each other. This minute difference, which came to be known as the Lamb shift, sent shock waves through the physics community. The Dirac equation, as beautiful as it was, had left something out. That missing element was the vacuum itself. When an electron orbits a proton inside a hydrogen atom, it does not move through a pristine, empty void. It is swimming through the sea of virtual particles that populate the electromagnetic field. The virtual electron-positron pairs that are constantly popping into and out of existence react to the presence of the real electron. The virtual positrons are slightly attracted to the real electron's negative charge, while the virtual electrons are slightly repelled. This process, known as vacuum polarization, creates a tiny shield around the real electron, slightly altering its effective electric charge and its magnetic moment. When physicists recalculated the energy levels of the hydrogen atom, factoring in the physical impact of this polarized vacuum foam, the theoretical predictions matched Willis Lamb's experimental measurements with exquisite, breathtaking precision. The Lamb shift provided definitive, unassailable proof that the empty space inside an atom has a tangible, measurable, physical presence. The vacuum is a participant in the behavior of matter. It actively pushes back against the electron, shifting its energy levels and changing the structure of the atom itself. Shortly after Lamb's discovery, a Dutch theoretical physicist named Hendrik Casimir proposed an even more direct and elegant way to expose the forces lurking within the vacuum. In 1948, Casimir calculated that if you take two uncharged, perfectly flat metal plates and place them incredibly close together in a complete vacuum, a strange thing should happen. The plates should be physically drawn together, pushed by an invisible, non-magnetic, non-gravitational force. To understand the logic behind the Casimir effect, we have to think about the vacuum fluctuations of the electromagnetic field as waves. In the open space outside the two plates, the quantum fluctuations can happen at any wavelength imaginable. Waves of every size can freely ripple through the vacuum. But in the tiny narrow gap between the two metal plates, space is constrained. Only waves that fit perfectly between the plates, wavelengths that can form standing waves, like the vibrations on a plucked guitar string, can exist inside that gap. Longer wavelengths are physically excluded. This creates a profound quantum imbalance. Because there are more allowed wavelengths of quantum fluctuations outside the plates than inside them, there are more virtual photons pushing on the plates from the outside than there are from the inside. The restless activity of the open vacuum surrounds the plates and drives them together. For decades, the Casimir effect remained a theoretical curiosity, because the technology required to place two plates close enough together without touching did not exist. But in the late 1990s, experimentalists successfully measured this force with immense precision. The vacuum of empty space exerts a literal physical pressure on objects, a direct consequence of the fact that it is teeming with quantum field activity. As we descend deeper into the heart of the atom, the illusion of empty space breaks down even more spectacularly. If we look past the electron cloud and focus our attention entirely on the nucleus, we encounter the protons and neutrons that give matter its substance and weight. In school, we are taught that a proton is made of three smaller particles called quarks, two up quarks and one down quark. This simple model makes it easy to understand electric charge, but it hides a shocking secret about where the mass of our world actually comes from. If you add up the individual masses of the 3 quarks that make up a proton, the sum accounts for a mere 1% of the proton's total mass. The remaining 99% of the mass of a proton, and therefore 99% of the mass of your body, your house, and the entire planet, is completely missing from the constituent particles. Where does this mass come from? The answer is pure energy, stored within the empty space inside the proton. Inside a proton, quarks are held together by the strong nuclear force, which is mediated by a field known as the gluon field. The gluons are the gauge bosons of the strong force, responsible for binding the quarks together with incredible intensity. Because the strong force operates via a principle called color confinement, the force between quarks does not get weaker as they move apart. It gets stronger, much like stretching a rubber band. This immense force means that the space inside a proton is filled with an incredibly dense, highly energetic gluon field. This field is so intense that it constantly fluctuates, birthing a roiling cloud of virtual gluons and virtual quark-antimatter quark pairs, known to physicists as the quark-gluon sea. The quarks are not sitting quietly inside the proton. They are tearing around at relativistic speeds, buffeted by a violent, high-energy storm of gluon field excitations. According to Einstein's principle of mass-energy equivalence, this intense kinetic and potential energy bound up within the field is physically manifested as mass. When you weigh an object on a scale, you are not weighing solid, heavy particles of matter. You are weighing the raw kinetic energy of fields, vibrating and fluctuating inside the empty spaces of the atomic nuclei. Matter, at its most fundamental level, is simply bound energy trapped within the localized field structures that we call protons and neutrons. To appreciate how these fields cooperate to construct our reality, we must look at the overarching framework that organizes them, the Standard Model of particle physics. The Standard Model is one of the most successful scientific theories ever created, describing all known fundamental forces except gravity, with astonishing mathematical predictive power. In this framework, the universe is built from 12 matter fields, known as fermions, and 4 force-carrying fields, known as bosons. The matter fields are split into 2 categories, quarks and leptons. The quarks include the up, down, charm, strange, top, and bottom fields. The leptons include the electron, muon, tau, and their corresponding 3 neutrino fields. These 12 fields are responsible for all the stable and unstable matter we observe in the universe. When you look at an atom, the up and down quark fields are excited to create the nucleus, while the electron field is excited to create the surrounding cloud. Intertwined with these matter fields are the force fields, which act as the messengers of the universe. The electromagnetic field, mediated by the photon, governs light, electricity, magnetism, and all of chemistry. The weak nuclear field, mediated by the W and Z bosons, is responsible for radioactive decay and the nuclear fusion processes that power the sun. The gluon field, as we have seen, manages the strong force that welds atomic nuclei together. Every single one of these fields occupies the exact same space simultaneously. The empty space between the atoms in your body is a multi-layered matrix, where the electron field, the up quark field, the down quark field, the electromagnetic field, and the gluon field are all perfectly superimposed. They are constantly whispering to one another, transferring energy, and shifting in response to the fluctuations of their neighbors. But for a long time, this beautiful mathematical framework faced a catastrophic flaw. According to the strict gauge symmetries that make the equations of the Standard Model mathematically consistent, all the fundamental particles in the universe should be entirely massless. The equations required the electron field, the quark fields, and the force fields to have no intrinsic mass whatsoever. This was an obvious existential problem for physics. If electrons and quarks had no mass, they would travel through the universe at the speed of light, completely unable to slow down, settle into orbits, or bind together to form atoms. The universe would be a chaotic, featureless spray of radiation, devoid of stars, planets, rocks, or living organisms. Something had to be operating within the vacuum to slow these fields down and give them weight. The solution to this crisis was proposed in 1964 by a small group of theoretical physicists, including the British physicist Peter Higgs. They suggested that the vacuum state of the universe is populated by yet another fundamental entity, the Higgs field. But the Higgs field possesses a unique, radical property that sets it apart from every other field in the standard model. For most fields, like the electromagnetic field or the electron field, the lowest energy state, the vacuum state, occurs when the field value is exactly zero. If you remove all charges, the electromagnetic field drops to zero and it becomes quiet. But the Higgs field does not work this way. Due to its unique mathematical structure, the Higgs field achieves its lowest energy state when its value is non-zero. Physicists often visualize this using a metaphor called the Mexican hat potential. Imagine a graph shaped like the bottom of a wine bottle or a sombrero, with a high peak in the center and a circular valley sloping down around it. The vertical axis represents energy, and the horizontal axis represents the value of the field. The center of the hat, where the field value is exactly zero, is actually a point of high potential energy, like a ball balanced precariously on the very tip of a sharp hill. If you release the ball, it will not stay at the top. It will spontaneously roll down into the circular valley below to find a stable, lower energy state. When the universe was born in the unimaginably hot flash of the Big Bang, the Higgs field sat at the center of the hat with a value of zero. All particles were massless and zipped through the cosmos at the speed of light. But as the universe expanded and cooled, the Higgs field underwent a dramatic phase transition. It slipped down from the peak into the valley, undergoing what physicists call spontaneous symmetry breaking. When the Higgs field settled into this valley, it took on a constant, non-zero value throughout the entire universe. This means that even in the deepest, coldest, most pristine vacuum between the galaxies, where every particle of matter and radiation has been stripped away, the Higgs field remains completely switched on. It fills the entire void with a uniform, invisible syrup. This non-zero vacuum expectation value of the Higgs field is what gives substance to our world. As the excitations of other fields, like the electron field or the quark fields, move through space, they are constantly interacting with this ambient Higgs field. The Higgs field drags on them, offering a subtle quantum resistance that slows them down and prevents them from traveling at the speed of light. This perpetual friction, this constant dragging through the quantum molasses of the vacuum, is what we macroscopically perceive as mass. An electron has mass because its underlying field couples tightly with the Higgs field filling the void. A photon has no mass because the electromagnetic field passes through the Higgs field completely unhindered, allowing it to fly at the ultimate cosmic speed limit. When you move your hand through the air, you are experiencing inertia, a resistance to change in motion. That inertia is a direct consequence of the subatomic fields inside your hand constantly interacting with the invisible Higgs field that saturates the empty space between your atoms. The discovery of the Higgs boson at the Large Hadron Collider at CERN in 2012 was the triumphant confirmation of this mind-bending reality. By colliding protons together at near-light speeds, physicists injected an immense amount of energy into a tiny patch of space, striking the ubiquitous Higgs field with enough force to create a localized ripple, a Higgs boson. The particle lasted for only a fraction of a second before decaying into other particles, but its brief presence confirmed that the cosmic molasses is real. We are swimming through an invisible ocean that gives us our physical form. This modern realization completely redefines our relationship with the universe. It forces us to discard the old, comfortable dualism of matter versus void. In the classical worldview, space was merely an empty container, a passive stage upon which the real entities, atoms and macroscopic objects, performed their cosmic dance. Space did nothing. It was simply the lack of things. But quantum field theory teaches us that space is an active, dynamic substance in its own right. It is the fields that are real, eternal, and all-pervading. What we call empty space is simply the state where these fields are operating at their baseline, minimum energy levels. What we call matter is not something separate from space. It is simply a vibrant, localized rearrangement of that very same space. You are not a collection of solid particles moving through an empty world. You are a complex, beautifully orchestrated symphony of field excitations temporarily condensed out of the very same universal vacuum that fills the vast distances between the stars. This perspective shifts how we view the macro-universe as well. If the empty space between atoms is full of fields, energy, and fluctuations, then the vast expanses of interstellar and intergalactic space are similarly crowded. When we look out at the deep cosmos and see billions of light-years of apparent nothingness separating the galaxies, we are looking at an arena that is teeming with the exact same quantum mechanics, the exact same zero-point energy, and the exact same Higgs field that governs our local reality. In fact, this energy of the vacuum has profound cosmological consequences that are currently dictating the ultimate fate of our universe. In the late 1990s, astronomers studying distant, exploding stars called Type Ia supernovae made an incredible discovery. They expected to find that the expansion of the universe, which began with the Big Bang, was gradually slowing down due to the collective gravitational pull of all the matter in the cosmos. Instead, the data revealed something entirely unexpected. The expansion of the universe is not slowing down, it is accelerating. Something is actively pushing the galaxies apart from one another at an ever-increasing rate, fighting against the pull of gravity on a cosmic scale. Physicists have named this mysterious repulsive force dark energy, and it constitutes roughly 68% of the total energy density of the universe. While the exact nature of dark energy remains one of the greatest unsolved mysteries in modern science, the leading candidate proposed by physicists is the cosmological constant, an idea originally introduced and then discarded by Albert Einstein. The cosmological constant represents the inherent energy density of empty space itself. In other words, dark energy may be nothing other than the macroscopic manifestation of the zero-point energy of our quantum fields. Because space is an intrinsic substance, when the universe expands, it does not dilute the vacuum. If you have a cubic meter of empty space, it contains a specific amount of quantum fields, zero-point fluctuations, and vacuum energy. When the universe expands and creates 2 cubic meters of empty space, the density of that vacuum energy remains exactly the same. The energy does not spread thin, it expands along with space, maintaining its constant push. As the universe grows larger, the total amount of matter remains fixed, meaning its gravitational pull grows weaker over time. But because the vacuum energy density stays constant, dark energy becomes increasingly dominant as space expands. It acts as a subtle, pervasive anti-gravity force inherent to the void, stretching the cosmos apart and guiding the universe toward a cold, isolated future where galaxies are swept away from one another faster than light can cross the distance between them. Yet, when physicists attempt to mathematically calculate the exact value of this vacuum energy using the rules of quantum field theory, they encounter a catastrophic problem that has been called the worst theoretical prediction in the history of science. If you add up the zero-point energy contributions from every single field wavelength allowed by quantum mechanics, the resulting theoretical value for the energy of the vacuum is unimaginably huge. It is roughly 10 to the power of 120 times larger than the actual amount of dark energy we observe in the cosmos. If the vacuum energy were truly that immense, the universe would have violently ripped itself apart in the first fraction of a second after the Big Bang. Atoms would never have been able to form, stars would never have ignited, and the cosmos would be completely unrecognizable. This gargantuan mismatch between theory and observation, known as the cosmological constant problem, reveals that while we have uncovered the profound truth that empty space is full, our current mathematical models are still missing a crucial piece of the puzzle. Perhaps there is some undiscovered symmetry in nature that cancels out the vast majority of the zero-point energy. Perhaps our understanding of gravity needs to be radically revised when applied to the quantum foam of the vacuum. Or perhaps, as string theorists suggest, our universe is just one tiny pocket within a vast, multi-dimensional multiverse, where different regions possess different vacuum energies, and we simply happen to live in a pocket where the vacuum energy is low enough to permit the existence of stable atoms and conscious observers. Regardless of how this mathematical crisis is eventually resolved, the conceptual reality remains unshaken. The old idea of the vacuum as a cold, dead, static emptiness has been permanently retired. The space between the atoms in your fingers, the space inside the glass of water on your desk, and the space stretching across the terrifying abysses of the cosmos is a living, breathing fabric. When you sit quietly in an empty room, you are not alone in a void. You are immersed in a hyperactive grid of overlapping cosmic fields. You are surrounded by a vacuum that is humming with baseline zero-point energy, vibrating with virtual particles that flash into and out of existence in the blink of an eye, and saturated by an all-pervading Higgs field that continuously gives mass and structure to every atom in your body. To understand modern physics is to realize that nothingness is one of the most interesting, complex, and vital substances in existence. The void is not the absence of reality. It is the fundamental matrix from which all reality is constructed. It is the canvas upon which the universe writes its story, and the source from which every particle, every force, and every conscious mind has ever emerged. Once you see the world through this lens, the illusion of emptiness vanishes, replaced by a profound appreciation for the invisible, eternal oceans of energy that fill every single point in our universe. This deep realization that the void is a dynamic fabric forces us to re-examine the historical trajectory that brought us here. We must look at the exact mechanics of how fields interact at the boundary lines, where empty space meets what we traditionally call solid matter. For centuries, the boundary of an atom was treated as a hard shell. When you push your hand against a wall, it feels like two solid objects are making physical contact, preventing one another from occupying the same location. But on the subatomic scale, nothing ever actually touches. When the atoms in your fingers approach the atoms in a wall, the vast expanses of empty space within those atoms never physically collide. Instead, the interaction is entirely a battle between fields. The electrons orbiting the nuclei of your fingers are excitations of the universal electron field, and they carry a negative electric charge. As they draw near the electron clouds of the wall, the electromagnetic fields filling the empty space between them begin to warp and intensify. The negative charges repel one another with tremendous force, governed by the Coulomb law. What you perceive as the solid resistance of a hard surface is not the impact of tiny material spheres. It is the palpable pushback of the electromagnetic field, an invisible barrier operating within the vacuum of the atom, resisting the compression of space. You are essentially floating on a cushion of electromagnetic force fields, suspended a fraction of a millimeter above the chair you sit on, separated by a microscopic pocket of intensely active, fluctuating space. To understand the sheer magnitude of this field-driven reality, we must look at how quantum fields behave when they are pushed to extremes, such as inside the crushing depths of a dying star. When a massive star runs out of nuclear fuel, it can no longer generate the outward radiation pressure needed to counteract the inward pull of its own immense gravity. The star begins to collapse, violently squeezing its atoms closer and closer together. In an ordinary atom, the empty space between the nucleus and the electron cloud is maintained by the laws of quantum mechanics. Specifically, it is preserved by the electron degeneracy pressure, a direct consequence of the Pauli exclusion principle. Because the universal electron field can only accommodate a fixed number of excitations in a given quantum state, the electrons resist being squeezed into the same spatial and energetic configurations. They push back against gravity, maintaining the vast, hollow architecture of the atom. But if the star is massive enough, gravity overcomes this barrier. The immense weight of the collapsing star forces the electrons to merge with the protons in the nucleus, transforming them into neutrons and releasing a torrent of neutrinos. The vast empty space inside the atoms is completely erased. The electrons are stripped of their expansive orbits, and the entire star collapses into a sphere just a few miles wide, a neutron star. A neutron star is so unimaginably dense that a single teaspoon of its material would weigh billions of tons on Earth. It is a macro object made almost entirely of pure atomic nuclei packed tightly together, with virtually all the internal atomic voids squeezed out. This demonstrates just how much of our everyday world is composed of that empty space. If you were to remove the empty space from within the atoms of every human being on Earth, compressing our fields until only the dense nuclei remained, the entire human race could fit inside the volume of a single sugar cube. We are quite literally ghosts made of space, given the illusion of solidity by the forces vibrating within the fields. If we push this cosmic compression even further, we arrive at the ultimate boundary of physics, a black hole. When a star is too massive for even the degeneracy pressure of neutrons to halt its collapse, gravity wins completely. It crushes the matter down into an infinitely dense point known as a singularity, surrounded by an invisible boundary called the event horizon. For decades, classical physics viewed a black hole as the ultimate sink, a region where space was so warped that nothing, not even light, could ever escape. It was imagined as an absolute, permanent void of information. But in 1974, the British physicist Stephen Hawking applied the principles of quantum field theory to the curved spacetime surrounding an event horizon, and he discovered something that once again turned our understanding of the vacuum upside down. Hawking realized that because the vacuum is not empty, but is constantly boiling with virtual particle pairs popping into and out of existence, the extreme gravitational field near a black hole's event horizon would disrupt this delicate quantum choreography. When a virtual particle-antiparticle pair spontaneously flashes into existence, right on the threshold of the event horizon, the immense gravitational tidal forces of the black hole can tear them apart before they have a chance to annihilate back into the underlying field. One of the virtual particles falls across the event horizon, trapped inside the black hole forever, but its partner, suddenly isolated on the outside, is left without a mate to annihilate with. It is cast adrift into the cosmos, transformed by the energy of the black hole's gravitational field, from a fleeting, virtual fluctuation into a real, permanent, positive energy particle. To an outside observer, the black hole appears to be glowing, emitting a faint, steady stream of radiation. This phenomenon, known as Hawking radiation, means that black holes are not completely black, and they are not eternal. They are slowly evaporating, leaking their mass back into the cosmos through the active manipulation of the quantum vacuum. The energy required to create this real, escaping particle is physically stolen from the black hole's own mass. The particle that falls inside effectively carries negative energy, reducing the total energy and mass of the black hole. Over unimaginable eons, if a black hole does not consume new matter, it will slowly shrink, losing mass faster and faster until it finishes its life in a violent, spectacular explosion of gamma rays. Hawking radiation provides a beautiful, terrifying example of how the vacuum is not a passive spectator. Even at the edge of a cosmic abyss, the fundamental fields of the void are capable of interacting with gravity to reshape the macroscopic architecture of the universe. This capacity of the vacuum to create and transform reality is not confined to the exotic environments of black holes or the subatomic interiors of atoms. It is the foundational mechanism that set our entire universe in motion. When cosmologists look back to the very beginning of time, to the epoch of the Big Bang, they are faced with a profound paradox. The universe we observe today is incredibly large, uniform, and flat, yet it contains minor ripples, slight variations in the density of matter that eventually clump together under gravity to form galaxies, stars, and planets. The leading scientific theory that explains this cosmic structure is called cosmic inflation, originally proposed by physicists like Alan Guth in the early 1980s. According to the inflationary model, in the first fraction of a microsecond after the birth of the universe, the cosmos underwent a period of blinding, exponential expansion, stretching space by a factor of at least 10 to the power of 26 in an instant. This rapid stretching was driven by a temporary, highly energetic quantum field known as the inflaton field. Before this expansion took place, the inflaton field was subject to the same fundamental laws that govern all quantum fields. It experienced spontaneous, microscopic quantum fluctuations. It hummed with the same tiny, jittering irregularities that we observe in the vacuum today. But when the universe underwent its sudden, violent inflationary burst, space expanded so fast that it grabbed these subatomic, fleeting quantum ripples and physically stretched them across macrocosmic distances. The tiny, microscopic fluctuations of the vacuum were frozen into the fabric of space-time itself, transformed from subatomic jitters into massive, light-years-wide variations in energy density. When inflation came to an end, the energy stored within the inflaton field decayed, dumping its contents into the other fields of the Standard Model, creating the hot, dense soup of quarks, electrons, and photons that we traditionally associate with the Big Bang. The regions of space that had slightly higher energy density, due to those stretched quantum fluctuations, became the cosmic seeds of our world. They possessed a slightly stronger gravitational pull, drawing in the surrounding matter over billions of years. These accumulated reservoirs of gas eventually collapsed to ignite the very first stars and gather the first galaxies. When astronomers look out into the deep night sky today and map the cosmic microwave background, the ancient, fading afterglow of the Big Bang, they see a beautiful, mottled pattern of hot and cold spots. That pattern is the literal, macroscopic fossil record of quantum fluctuations that occurred within the vacuum at the dawn of time. Every galaxy in the cosmos, every star system, and the very planet we stand on owes its existence to the random, subatomic jitters of a quantum field that operated billions of years ago. We are living inside the magnified architecture of the quantum void. This realization forces a profound philosophical shift in how we conceptualize existence. For millennia, humanity operated under the assumption of a stark binary, being versus non-being, matter versus nothingness. We treated matter as the active, creative principle and the void as a sterile absence. But the deeper we probe into the structure of reality, the more this boundary blurs, until we see that the vacuum is the primary generator of everything we know. Consider the phenomenon of spontaneous symmetry breaking, which we examined through the lens of the Higgs field. This process is not a rare exception. It is a recurring theme in the history of the universe. As the early cosmos cooled, multiple fields underwent transitions, shifting from symmetric states of high energy to broken states of lower energy, forever altering the laws of physics in the process. It is helpful to visualize this using a classical analogy, like a drop of liquid water cooling down to form ice. When water is in its liquid state, it is highly symmetric. If you were microscopic and swam through a drop of water, the arrangement of molecules would look roughly the same in every direction. There is no preferred orientation. But when the temperature drops past the freezing point, the water molecules spontaneously lock into a rigid crystalline lattice to form ice. This crystal structure breaks the original symmetry of the liquid. Now there are specific directions aligned with the axes of the crystal. The ice has properties that the liquid water did not possess. It can resist shear stress, it cleaves along specific planes, and it refracts light differently. The properties of the ice are not inherent to the individual water molecules themselves, but are a consequence of the structure that emerged when the system settled into its lower energy state. The fields of our universe broke their symmetries in a similar fashion during the cooling phases of the early cosmos. The electromagnetic field and the weak nuclear field were originally part of a single, unified force known as the electroweak force. In that high-energy era, the photons and the W and Z bosons were all completely massless, indistinguishable from one another in their behavioral mechanics. But as the universe expanded and the temperature dropped, the Higgs field underwent its phase transition, settling into the valley of the Mexican Hat potential. This act of vacuum settlement fractured the electroweak force into the two distinct phenomena we observe today. The electromagnetic field remained uncoupled from the Higgs vacuum expectation value, keeping the photon massless and allowing it to transmit light across infinite distances. The weak nuclear field coupled tightly to the Higgs vacuum, causing the W and Z bosons to become heavy and sluggish, restricting the weak force to the ultra-short ranges of the atomic nucleus. The very laws of nature, the strengths of the forces, the masses of the particles, and the stability of chemistry are not hard-coded into the universe as immutable constants. They are environmental properties established by the specific configurations that the quantum fields adopted when they settled into their vacuum states. If you could somehow inject an immense amount of energy into a region of space, heating it up to the temperatures of the early universe, you could melt the vacuum, restoring the broken symmetries and altering the behavior of matter within that zone. The vacuum is a repository of hidden laws, a structured template that shapes the behavior of everything caught within its grip. This structural complexity of the void is further highlighted by a phenomenon known as the Unruh effect, proposed by the Canadian physicist William Unruh in 1976. The Unruh effect introduces a truly startling concept. What one observer sees as an empty vacuum, another observer may see as a hot, crowded bath of particles, depending entirely on their state of acceleration. According to quantum field theory, an observer sitting at rest in a complete vacuum will measure the fields to be in their lowest energy state. They will detect no real particles, only the baseline zero-point fluctuations. But if another observer accelerates through that very same piece of space with a tremendous, constant acceleration, the mathematics of special relativity and quantum mechanics interact in a strange way. To the accelerating observer, the boundary lines of space-time shift, creating a horizon that cuts them off from certain regions of the universe. This horizon distorts their perception of the quantum fluctuations. When they look at the vacuum around them, their instruments will not register a cold, empty void. Instead, they will detect a warm, thermal bath of real photons, electrons, and other particles flying at them from every direction. The temperature of this bath is directly proportional to their acceleration. The Unruh effect demonstrates that the concept of a particle is not an absolute, observer-independent fact. A particle is a relational property, an excitation of a field defined relative to a specific frame of reference. What is an empty, unexcited vacuum to a person sitting still is a roiling, burning furnace of matter to a person accelerating through it. The line between nothing and something depends entirely on how you move through the world. The void is a kaleidoscope of potentials, waiting to manifest differently depending on the perspective of the observer. This fluid relationship between empty space and matter is what makes the study of quantum field theory so intellectually destabilizing. It dismantles the mechanical, clockwork universe of the Enlightenment, replacing it with a reality that is deeply interconnected and holistic. In the old Newtonian paradigm, you could isolate a particle of matter, remove it from its environment, and study it as an independent object. The environment was just the empty stage. But in the quantum field paradigm, you can never truly isolate a particle from its environment, because the particle is the environment. An electron cannot exist without its field, and its field is inextricably linked to every other field in the cosmos. When an electron moves through space, it is constantly interacting with the virtual particles of the electromagnetic field, the Higgs field, and the gravitational field. It is continuously dressing itself in a cloud of vacuum fluctuations. When physicists calculate the properties of an electron, such as its mass or its electric charge, they find that the bare electron, the hypothetical particle stripped of its vacuum cloud, possesses an infinite mass and an infinite charge. These infinities arise because the closer you get to the center of an electron excitation, the more violent and energetic the vacuum fluctuations become. The energy density skyrockets toward infinity. To resolve these mathematical infinities and make sense of the real world, physicists developed a technique called renormalization. Renormalization is a process of mathematical subtraction, where the infinite energy of the bare particle is balanced against the infinite energy of the surrounding vacuum fluctuations. The result of this delicate mathematical dance is the finite, stable values we measure in the laboratory, the specific mass and charge of the electron that makes chemistry possible. This means that the properties of matter are not self-contained. The mass of an electron is a collective property, a negotiated settlement between the localized excitation of the electron field and the infinite sea of fluctuations that surrounds it. Matter is a partnership with the void. You cannot have a piece of matter without invoking the entire system of fields that spans the universe. As we look to the future of physics, this study of the vacuum remains the central frontier where the next great scientific revolution will likely occur. Currently, physics is paralyzed by a profound schism between our two most successful theories: quantum field theory, which describes the subatomic world of forces and particles, and general relativity, which describes the macroscopic world of gravity and curved spacetime. These two theories speak entirely different mathematical languages. Quantum field theory operates on a flat, static spacetime background, where fields fluctuate violently at small scales. General relativity operates on a smooth, continuous spacetime fabric, where gravity responds to mass and energy without any quantum fuzziness. When you try to combine them, to calculate the gravitational effect of the violent quantum fluctuations inside the vacuum, the math breaks down completely, yielding the disastrous cosmological constant problem we discussed earlier. To heal this rift, physicists are searching for a theory of quantum gravity, a framework that can describe the quantum structure of spacetime itself. Promising candidates like string theory and loop quantum gravity suggest that if we could zoom in past the scale of quarks and electrons, past the scale of virtual particles, down to the ultimate limit of distance known as the Planck scale, we would find that spacetime is not a smooth fabric at all. At the Planck scale, the gravitational field itself becomes subject to intense quantum uncertainty. Space and time lose their continuous, smooth character and dissolve into a chaotic, twisting, subatomic froth known as quantum foam. At this scale, the very concepts of before and after, here and there, cease to have any meaningful definition. Space-time becomes quantized, broken down into fundamental units, perhaps tiny vibrating strings of energy or interconnected loops of geometry. In this picture, what we call empty space is not just full of fields. It is itself a dynamic, living network of quantum connections. The fields do not merely inhabit space. They are woven out of the same fundamental quantum threads that constitute space itself. Matter, energy, forces, and space-time are all revealed to be different geometric vibrations of a single, underlying cosmic substance. This brings us to the ultimate conclusion of our journey into the void. The next time you look out into a clear night sky and marvel at the cold, immense vacuum separating the stars, or the next time you contemplate the vast invisible spaces operating within the very atoms of your own body, remember that you are not looking at nothingness. You are looking at the most crowded, active, and creative structure in the universe. You are looking at a tapestry woven from overlapping quantum fields, humming with an unquenchable zero-point energy, and pulsing with the spontaneous birth and death of matter and antimatter pairs. You are looking at the invisible syrup of the Higgs field, giving weight and stability to the material world, and the mysterious pressure of dark energy guiding the expansion of the cosmos. The empty space between atoms is not a void, it is the source. It is the fundamental matrix that sustains our existence, the quiet ocean whose surface ripples manifest as the solid, vibrant world we experience every day. Matter is not the opposite of nothingness. It is simply the vacuum made visible. We are children of the void, shaped by its hidden architectures, dancing to the rhythms of its eternal subatomic song. This recognition that space is a structural tapestry, a vibrant, multi-layered canvas woven from quantum fields, fundamentally upends our concept of locality and separation. In our day-to-day macro existence, things seem isolated. A planet spins in its orbit, separate from the star it circles. A molecule floats across a room, independent of the furniture. A human being stands alone, a self-contained island of matter. But once we peer through the lens of quantum field theory into the atomic void, the very concept of isolation dissolves. Because the fields are continuous and universal, every single point in the universe is structurally hooked into every other point. The electron field that vibrates within an atom in your eye is the exact same, unbroken, cosmic sheet that vibrates to create an electron in a distant galaxy on the edge of the observable universe. There are not trillions of separate electrons scattered across the void. There is only one universal electron field, and every electron in existence is a localized ripple playing out on that single, all-encompassing sheet. To understand the profound implications of this interconnected field reality, we must venture into one of the most hauntingly beautiful phenomena in all of physics: quantum entanglement. In the popular imagination, entanglement is often described as a mystical, telepathic connection between two distant particles. If you entangle two electrons and send one to the opposite side of the planet, measuring the spin of one instantly determines the spin of the other, defying the cosmic speed limit of light. Albert Einstein famously rejected this idea, deriding it as spooky action at a distance. He believed that it violated the core principles of his relativity theory, which declared that no signal or influence could travel faster than light. But this paradox only arises if we cling to the outdated classical view that particles are independent, self-contained entities flying through a barren vacuum. When we shift our perspective to quantum field theory, the spookiness disappears, replaced by a deep geometric logic. In the field framework, the two entangled electrons are not separate objects separated by thousands of miles of empty nothingness. They are two localized excitations belonging to the exact same, continuous universal electron field. When we entangle them, we are not establishing a hidden radio link between two distant points. We are twisting a single, underlying fabric. The correlation between them is preserved because the field itself remains unified across that vast distance. The empty space separating the two electrons is not a barrier that cuts them off from one another. It is the very medium that connects them. The measurement of one excitation instantly reflects in the other because you are interacting with a single holistic system that spans the entire distance. The universe, at its core, does not know separation because the fields filling the void remain completely whole, binding the farthest reaches of the cosmos into a singular, unbroken web of relation. This continuous nature of the quantum vacuum can be visualized by examining a macroscopic phenomenon that mirrors this subatomic architecture: the behavior of superfluids. If you take a gas of helium atoms and cool it down to temperatures agonizingly close to absolute zero, a dramatic transformation occurs. The individual atoms lose their localized identities. Their quantum wave functions expand and overlap until they merge into a single macroscopic quantum state known as a Bose-Einstein condensate. A superfluid behaves like a single, giant quantum object. It possesses zero viscosity, meaning it can flow through microscopic cracks without experiencing a single shred of friction. If you set a superfluid in motion inside a ring-shaped container, it will circulate forever, never slowing down, never losing energy to its environment. If you leave a superfluid in an open beaker, it will spontaneously crawl up the inner walls of the glass, defy gravity, slide down the outside, and drip off the bottom, until the container is completely empty. The reason a superfluid behaves this way is because its constituent parts have achieved perfect coherence. They are vibrating in flawless harmony, acting as a single, unified field. This macroscopic coherence gives us a tangible, visible preview of what the quantum vacuum is doing on a fundamental level at every moment. The vacuum filling the empty space between atoms is essentially a universal, cosmic superfluid. It is a coherent, low-energy state of fields that flows through everything without friction, resisting disruption, and maintaining its baseline structure across billions of light-years. Matter does not collide with the vacuum as it moves through space because the vacuum is already in its ground state. It cannot drop any lower, and it cannot absorb energy through ordinary friction. The planets glide through the interstellar void with perfect ease because they are swimming through a frictionless quantum fluid that is completely adapted to their passage. But this cosmic fluid can be disturbed if we subject it to extreme, accelerated conditions, giving rise to another mind-bending concept known as the dynamical Casimir effect. We have already seen how the static Casimir effect pushes two motionless plates together because certain virtual particle wavelengths are excluded from the narrow gap between them. The dynamical Casimir effect takes this principle into the realm of motion. If you take a mirror and shake it back and forth through a vacuum at relativistic speeds, accelerating it so violently that its velocity approaches the speed of light, a remarkable thing happens. The mirror begins to collide with the virtual photons that inhabit the quantum vacuum. Normally, these virtual particles flash into existence and disappear so rapidly that they cannot be directly intercepted. But if the mirror moves fast enough, it can physically separate the virtual photon pairs before they have a chance to recombine and annihilate back into the background field. The mirror pumps its own mechanical kinetic energy into the vacuum fluctuations, converting those fleeting, invisible virtual photons into real, permanent, measurable pulses of light. The empty space in front of the violently shaking mirror literally begins to glow, radiating real photons out into the room. This extraordinary phenomenon was successfully demonstrated in laboratory experiments in 2011 using superconducting circuits that simulated a mirror moving at a significant fraction of the speed of light. It stands as a triumphant vindication of the active reality of the void. You can manufacture light out of absolute darkness simply by agitating the underlying electromagnetic field with enough violence. The vacuum is a reservoir of unmanifested light, waiting for the right mechanical catalyst to coax its hidden energy into the visible world. As we look at these various ways the vacuum manifests, we must confront a profound historical irony. For centuries, the progress of science was defined by the systematic destruction of the ancient concept of the ether. When 19th century physicists like Maxwell discovered that light was a wave, they assumed it must require a material medium to ripple through, just as sound waves require air, and ocean waves require water. They called this hypothetical substance the luminiferous ether, imagining it as an incredibly rigid, yet invisible fluid that filled all of space, providing the physical tracks upon which light waves traveled. In 1887, two American scientists, Albert Michelson and Edward Morley, set out to detect this ether using a highly sensitive instrument called an interferometer. They reasoned that as Earth hurtled through space in its orbit around the Sun, it should experience an ether wind. Light traveling in the same direction as Earth's motion should move at a slightly different speed than light traveling perpendicular to it. To the absolute astonishment of the scientific community, the Michelson-Morley experiment returned a definitive null result. The speed of light was exactly the same in every direction, regardless of Earth's motion. There was no ether wind. Space was not filled with a material fluid dragging against our planet. This historic experiment paved the way for Albert Einstein's special theory of relativity, which discarded the ether entirely, demonstrating that light travels at a constant speed through a complete vacuum without needing any material tracks to carry it. The ether was dead, dismissed as a primitive scientific myth. But as quantum field theory matured throughout the 20th century, physicists realized that in killing the classical ether, they had inadvertently birthed something remarkably similar, though infinitely more subtle and profound. The modern quantum vacuum, populated by a network of overlapping fields, zero-point energies, and the pervasive Higgs field, is essentially a quantum ether. It is an all-pervading, invisible medium that fills every nook and cranny of the cosmos, dictating the masses of particles, mediating the forces of nature, and humming with continuous activity. The crucial difference between the old classical ether and the modern quantum vacuum is that the quantum vacuum is fully compatible with relativity. The classical ether was imagined as a material substance with a specific frame of rest. If you moved through it, you could measure your speed relative to it. The quantum vacuum, however, is a non-material Lorentz invariant state. Because it is the lowest energy state of quantum fields, it looks exactly the same to every observer, regardless of how fast they are moving. Whether you are sitting perfectly still in a laboratory or blasting through space at 99% the speed of light, the baseline zero-point fluctuations of the vacuum will appear completely identical. It is an ether that respects the laws of relativity, a medium that fills all of space without establishing a preferred frame of rest. The ancient intuition that space must be filled with a fundamental, organizing substance was not entirely wrong. It was simply waiting for the language of quantum mechanics to state its true form. To fully grasp how this quantum ether dictates the architecture of the material world, we can look at a beautiful concept known as vacuum engineering. Because the properties of particles, their masses, their lifetimes, and their interaction strengths, are determined by their relationship with the surrounding fields, if you can artificially alter the structure of the vacuum in a localized region, you can change the very laws of physics within that zone. This is not science fiction. It is an active area of research in modern physics known as cavity quantum electrodynamics, cavity QED. Imagine placing an excited atom inside a tiny, highly reflective metallic cavity. When an atom is in an excited state, it naturally wants to drop down to a lower energy level, releasing its excess energy by emitting a photon. In ordinary open space, this process of spontaneous emission happens at a predictable, statistical rate. The atom interacts with the baseline fluctuations of the open electromagnetic field, which coaxes the atom into releasing its photon. But inside the narrow confines of the metallic cavity, the vacuum is altered. Just like in the Casimir effect, the walls of the cavity physically forbid electromagnetic fluctuations at wavelengths that do not fit perfectly within its dimensions. If you design the cavity so that its size is smaller than the wavelength of the photon the atom wants to emit, the vacuum inside the cavity will contain absolutely zero field fluctuations at that specific frequency. The quantum vacuum at that exact wavelength is completely dead. When the excited atom sits inside this engineered void, it cannot emit its photon. The virtual photons required to trigger the spontaneous emission are missing from the environment. The atom becomes trapped in its high-energy state, its lifetime extended indefinitely. It wants to decay, but the vacuum will not allow it. Conversely, if you tune the cavity so that its dimensions perfectly match the photon's wavelength, the vacuum fluctuations at that frequency will be dramatically amplified. The atom will release its photon at an accelerated rate, dropping its energy much faster than it ever could in the open world. Cavity QED demonstrates that the fundamental behavior of matter is not set in stone. An atom's internal transitions are directly dependent on the state of the void it inhabits. By manipulating the boundaries of empty space, we can engineer the quantum environment, controlling the interactions between matter and light with exquisite precision. This technology is currently being used to develop ultra-precise atomic clocks, highly efficient quantum sensors, and the fundamental hardware needed to build scalable quantum computers. The vacuum is a machine, and by adjusting its structural dimensions, we can change the behavior of the material world. This capacity to manipulate the vacuum points toward an even grander, more speculative frontier in theoretical physics, the concept of false vacuum decay. To understand this cosmological threat, we must return to the structure of the Higgs field and its Mexican hat potential. We saw that the Higgs field currently sits in a stable valley, possessing a non-zero vacuum expectation value that fills the cosmos and gives mass to particles. Physicists call this current state the true vacuum, the lowest accessible energy configuration of our universe. But what if the valley our Higgs field settled into is not the absolute lowest point on the graph? What if it is a local minimum, a shallow depression on the side of a much deeper, grander valley that lies hidden behind a high mathematical ridge? If this is the case, our universe currently exists in what is known as a false vacuum. It feels stable, and it has remained stable for 13.8 billion years, but it is fundamentally metastable, like a snowdrift balanced precariously on the edge of a steep mountain cliff. According to classical physics, if a system is trapped in a local minimum behind a high barrier, it can never escape unless it receives a massive injection of external energy to push it over the top. But in the quantum realm, particles and fields can bypass barriers through a phenomenon known as quantum tunneling. There is a tiny, non-zero probability that at any moment, at some random point in the cosmos, the Higgs field will spontaneously tunnel through the mathematical ridge, slipping down into the deeper, absolute minimum of the true vacuum. If this quantum tunneling event occurs, it will trigger a catastrophic cosmological chain reaction. The tiny bubble of true vacuum will have a much lower energy density than the surrounding false vacuum. This immense energy differential will cause the bubble to expand outward in all directions at the absolute speed of light. As the wall of this vacuum bubble sweeps through space, it will fundamentally rewrite the laws of physics in its wake. The non-zero value of the Higgs field will change instantly, altering the masses of all fundamental particles. Inside the expanding bubble, electrons will become heavy or light, quarks will unbind from their protons, and the electromagnetic force will warp into something completely unrecognizable. Atoms will instantly dissolve, chemistry will become impossible, and all material structures, from planets to living organisms, will be obliterated in a fraction of a microsecond without warning. This concept, known as the vacuum metastability disaster or the Big Slurp, is one of the most dramatic ways the universe could end. Recent measurements of the mass of the Higgs boson and the top quark suggest that our universe may indeed be sitting in a false vacuum, hovering on the brink of this cosmic instability. Fortunately, the calculated lifetime of our false vacuum is extraordinarily long, billions of trillions of years greater than the current age of the universe, meaning the probability of a tunneling event happening in our lifetimes is comforting close to zero. Yet, the mere fact that such a phenomenon is mathematically possible reveals just how completely we are at the mercy of the void. The stability of our existence, the rigidity of our bones, and the burning of the sun are all balanced on the specific, temporary arrangement of a universal field sitting in a specific valley of energy. The vacuum is the ultimate arbiter of cosmic destiny. If it shifts its posture by a single degree, the entire material world is instantly erased. This realization that matter is completely subservient to the fields of the void transforms our understanding of the grand life cycle of the cosmos. It forces us to look past our anthropocentric focus on solid objects and see that the history of the universe is fundamentally the history of the vacuum's evolution. When the universe was young, hot, and packed tightly into a tiny volume, the fields were wild, symmetrical, and bursting with raw energy. As space expanded, the vacuum cooled, undergoing the phase transitions that fractured forces, froze out mass, and established the quiet, baseline matrix we see today. We are currently living in a golden, temporary epoch of cosmic history, where the vacuum is stable enough to permit the complex configurations of matter that we call chemistry, geology, and biology. The excitations of the fields have organized themselves into intricate, self-replicating patterns, forming the neurons in your brain that are currently processing these very words. We are the vacuum become conscious. We are the universal fields, waking up, looking back at themselves, and trying to decode the very mechanisms that allow them to exist. This perspective offers a profound sense of grounding, an authentic validation of our deep connection to the cosmos. In the classical worldview, humanity was often depicted as a tragic accident, a fragile material anomaly stranded in a cold, vast, uncaring void that was completely alien to our nature. We were things in space, struggling to survive against a hostile nothingness. But quantum field theory heals this existential alienation. It teaches us that there is no division between you and the void. The empty space inside your body is made of the exact same substance as the empty space separating the stars. The fields that construct your flesh are the exact same fields that span the entire cosmos. You are not a foreign object trying to navigate an empty world. You are an organic expression of the space itself. When you look at a star in the night sky, you are not just looking across an empty distance at a distant object. You are looking through a continuous, universal electromagnetic field that connects your eye directly to that star. The light you receive is a ripple that has traveled across a single, unified cosmic sheet, bridging the immense chasm of space without ever leaving the medium that binds you together. The universe is not a collection of isolated fragments. It is an integrated, humming, holistic organism, and the vacuum is the vital nervous system that coordinates its behavior. As we look toward the final horizons of scientific exploration, the mystery of the vacuum remains the ultimate prize. Every great question in modern physics, from the nature of dark energy and dark matter to the origin of the Big Bang and the unification of quantum gravity, is fundamentally a question about the properties of empty space. We are like deep-sea fish, swimming through an invisible ocean, gradually becoming aware of the water that surrounds us. We have climbed a tremendous mountain of intellectual history to reach this vantage point. We started with the ancient Greeks, who argued that a vacuum was a logical impossibility, a contradiction in terms that nature would never allow. We traced the experimental breakthroughs of the 17th century, where scientists like Torricelli, Pascal, and von Guericke physically pumped the air out of glass chambers, shattering the old dogmas and exposing the tangible weight of our atmosphere. We witnessed the visual genius of Faraday and the mathematical mastery of Maxwell, who populated that mechanical vacancy with the invisible architecture of fields, proving that light could travel through the void because it was a ripple in the fabric itself. Then, we experienced the radical double punch of the 20th century, quantum mechanics and relativity. Quantum mechanics showed us that fields cannot rest, that the uncertainty principle condemns the vacuum to a perpetual baseline hum of zero-point energy and virtual particle creations. Relativity showed us that space-time is a dynamic, geometric field that bends, curves, and expands in response to energy. Together, they forged quantum field theory, revealing that particles are not solid pellets of matter, but are simply the localized, vibrant crests of vast, universal field oceans that fill the cosmos from edge to edge. We discovered that 99% of the mass in your body is not found in solid material, but is the raw kinetic energy of fields churning within the empty spaces of your atomic nuclei. We learned that we are swimming through a pervasive Higgs field molasses that slows us down and gives us weight, and that the ultimate fate of our universe is currently being driven by the dark energy hidden within the vacuum's expanding pressure. This is the strangest, most beautiful truth in all of physics. Empty space is not empty. It is a crowded, dynamic, and vital reality. It is the canvas, the actor, the force, and the substance all at once. The next time you look at the seemingly vacant spaces around you, let the illusion of emptiness fall away. See the invisible webs of the electromagnetic field, vibrating with potential. Feel the gentle drag of the Higgs field, giving mass to your form. Hear the silent, subatomic hum of the zero-point fluctuations jittering at every point in the room. The void is not nothingness. It is the fullness of being, an eternal, restless ocean of energy from which our entire world has condensed. and into which it will eventually return. Once you understand what the fields are and what they do, you will never look at empty space, at matter, or at reality itself the same way again. To truly push the boundaries of this paradigm shift, we must venture into the microscopic geometry where the fields of the vacuum encounter the extreme mathematical boundaries of space-time itself. When we step back and look at how these universal sheets operate, we begin to realize that the behavior of the atomic void is deeply governed by a principle that sounds like it belongs in the realm of optical illusions, the holographic principle. Developed by theoretical physicists like Gerard 't Hooft and Leonard Susskind in the 1990s, and later refined by Juan Maldacena, this radical idea suggests that everything we experience in three-dimensional space, including the empty space between our atoms and the particles vibrating within them, might actually be a projection. It could be a microscopic manifestation of information that is stored on a distant, two-dimensional boundary wrapping around the ultimate horizon of the universe. To understand how this alters our picture of the atomic void, we have to look at what happens when you try to cram an immense amount of information into a tiny region of space. In classical computer science, information is stored in bits, which require physical material to exist, whether it is the alignment of magnetic domains on a hard drive or the state of transistors in a silicon chip. If you want to store more data, you need more volume. Naturally, physicists assumed that the maximum amount of quantum information you could store inside a room, an atom, or any region of space was directly proportional to the volume of that region. But when physicists tried to calculate the ultimate data storage limit of nature, using the rules of quantum field theory and black hole thermodynamics, they hit an astonishing mathematical wall. If you take a region of space, say the tiny space inside a single gold atom, and you try to pack more and more information into it by injecting high-energy particles, you will eventually add so much energy and mass to that tiny volume that gravity will collapse it. The atom will instantly morph into a microscopic black hole. Once that black hole forms, any additional information you try to throw into it will not increase the volume of the black hole. Instead, it increases the surface area of its event horizon. The total information content of that region of space becomes strictly locked to the two-dimensional boundary of the horizon, not the three-dimensional space inside. This realization led to a mind-blowing insight. The total information capacity of any three-dimensional volume of empty space is not determined by its volume at all. It is determined entirely by its surface area. The three-dimensional world of our everyday experience, the universe of macroscopic objects, stars, and the empty space between atoms, is an illusion. It is a cosmic hologram, projected from a two-dimensional matrix of information encoded at the boundary of reality, explains Susskind, summarizing the conceptual shock of the holographic framework. If the information that defines the behavior of fields inside an atom is actually written on a distant, lower-dimensional boundary, then our traditional concept of the atomic void must be completely rewritten. The empty space separating the nucleus from the electron cloud is not a real, independent, three-dimensional container. It is a reconstructed projection, a structural rendering emerging from the complex quantum entanglement of information taking place on a boundary. If you were to alter the entanglement pattern of the pixels on that distant boundary, the fields inside the atom would instantaneously warp, shifting the positions of electrons or changing the strength of the forces. The void is not a localized vacancy. It is an emergent holographic display. What we perceive as a vast, hollow architecture inside the atom is simply the macroscopic language that our minds use to interpret a deeply interconnected, low-dimensional web of quantum data. This holographic nature of space becomes even more profound when we look at how the vacuum manages the concept of symmetry and topology through things called topological solitons or instantons. In our previous explorations, we visualized quantum fluctuations as random, fleeting jitters, waves that ripple across the surface of a field and quickly vanish. But the mathematics of quantum field theory reveals that fields can also form stable, knotted structures in empty space that cannot be easily undone. These are not ordinary particles. They are localized distortions in the very geometry of the vacuum. Imagine a long, heavy rope pinned down at both ends. If you pluck the rope, you create a wave that travels down its length and dissipates. This is like a standard particle excitation. But now, imagine taking one end of the rope, giving it a full 360-degree twist, and then pinning it back down. You have created a physical twist, a knot that is trapped in the rope. You can slide the twist back and forth along the rope, and it will carry energy and momentum, behaving exactly like a solid object. But you cannot flatten it out simply by pulling on the rope. To get rid of the twist, you would have to physically unpin one end of the rope and untwist it. In the language of physics, this twist is topologically stable. The quantum fields filling the empty space between atoms can form these exact kinds of topological knots. In the gluon field that binds quarks together inside a proton, these stable field configurations are known as instantons. An instanton is a localized, non-perturbative solution to the field equations that represents a transition between different topological states of the vacuum. Instantons are not material objects made of separate parts. They are pure structural geometries carved out of the vacuum itself. They act as invisible stepping stones, allowing the strong nuclear field to tunnel between different energy configurations that would otherwise be completely inaccessible. The presence of these instanton knots inside the atomic nucleus directly influences the masses of particles and governs the subtle symmetries of the strong force. The empty space within a proton is not a smooth, featureless fluid. It is a complex, knotted labyrinth of field topology, twisted into permanent structures that prevent the building blocks of matter from dissolving into a chaotic spray of energy. To fully grasp how these deep field geometries organize the physical world, we can look at an extraordinary concept that links the micro-void of the atom directly to the macro-void of the cosmos: cosmic strings. Not to be confused with the subatomic strings of string theory, cosmic strings are hypothetical macroscopic defects in the fabric of space-time that may have formed during the rapid cooling phase transitions of the early universe. When we looked at spontaneous symmetry breaking, we used the analogy of water freezing into ice, forming a rigid crystalline lattice. But if you watch a tray of water freeze closely, you will notice that the ice does not form as a single, flawless, perfect crystal. Instead, the freezing process begins simultaneously at dozens of different random locations throughout the tray. As these individual ice crystals grow outward, their molecular orientations do not match up cleanly. When the expanding crystals finally slam into one another, they form visible cracks, seams, and imperfections trapped inside the solid block of ice. When the quantum fields of the early universe underwent their phase transitions, dropping down into their lower energy vacuum states, they broke their symmetries independently in different regions of the rapidly expanding cosmos. As these distinct domains of space settled into their new configurations, they encountered alignment mismatches at their boundaries. The resulting seams, trapped forever within the vacuum of space, are cosmic strings. A cosmic string is an unimaginably thin line of raw, unbroken, high-energy false vacuum traversing the expanse of the universe. They are thought to be thinner than a single proton, yet a single mile of a cosmic string would weigh more than the entire Earth. They possess immense gravitational tension, bending the very geometry of space-time around them into a distinct conical shape. If you were to look past a cosmic string at a distant galaxy, the warped space around the string would act as a powerful gravitational lens, splitting the light to create two identical, perfect twin images of the same galaxy, side by side in the night sky. While astronomers are still actively scanning the deep cosmos for definitive observational proof of these structural seams, their theoretical existence underscores a vital truth about the nature of emptiness. The vacuum is a historical entity, an environmental ledger that bears the permanent physical scars of its ancestral evolution. The vast spaces separating the galaxies, and by extension the tiny spaces operating within our local atoms, are not pristine, virgin voids. They are cracked, seamed, and structurally patterned landscapes, molded by the violent transitions that occurred when the universe was cooling down to establish the baseline of our current reality. This historical, structured nature of the vacuum becomes even more intimate when we examine the concept of vacuum birefringence, a phenomenon that directly demonstrates how empty space can act as a physical lens, distorting light in the presence of intense magnetic fields. According to classical electrodynamics, light waves pass through one another in a vacuum without any interaction. If you cross two flashlight beams in a dark room, the photons pass straight through each other without bouncing off, colliding, or altering their paths. The classical void has no refractive index. It is completely passive. But in the realm of quantum electrodynamics, QED, the roiling sea of virtual electron-positron pairs changes the rules of the game. When a strong magnetic field is applied to a region of empty space, it interacts with these virtual particles. Because electrons and positrons carry electric charges, the intense magnetic field forces them to align themselves, polarizing the vacuum. The virtual pairs line up like tiny subatomic compass needles, transforming the empty space into a highly structured anisotropic medium. When a beam of real light attempts to travel through this magnetically charged void, it encounters this polarized matrix of virtual particles. Light waves vibrating parallel to the magnetic field lines will experience a slightly different resistance than light waves vibrating perpendicular to them. The empty space physically splits the light, causing the two components to travel at slightly different speeds, a phenomenon known as birefringence. In 2016, astronomers, using the Very Large Telescope in Chile, observed this exact effect occurring in the empty space surrounding a neutron star named RxJ 1856.53754. This dead stellar core possesses a magnetic field billions of times stronger than anything we can manufacture on Earth. As the light from distant stars passed through the extreme vacuum immediately surrounding the neutron star, its polarization was distinctly altered, matching the precise mathematical predictions of vacuum birefringence. This discovery proved that empty space can be manipulated to possess a literal refractive index. The vacuum can bend, polarize, and sculpt light just like a physical prism of glass or a drop of water. It is a material medium in everything but name, possessing mechanical and optical properties that can be unlocked if you subject it to enough environmental force. This optical plasticity of the vacuum points toward an even crazier, more sci-fi manifestation of quantum field mechanics known as the Schwinger effect. Named after the Nobel laureate Julian Schwinger, who mathematically formalized the idea in 1951, the Schwinger effect describes a threshold where the vacuum breaks down completely, ripping matter directly out of the void without needing any initial particles to collide. To understand how this works, we have to look at the electric field strength required to physically disrupt a virtual electron-positron pair before they can annihilate back into the background field. Normally, these virtual particles are bound together by an intense quantum attraction, existing for only a fleeting fraction of a second. But if you apply an external electric field to a patch of empty space, that field will exert an opposite force on the virtual pair. It will pull the negatively charged virtual electron in one direction and the positively charged virtual positron in the exact opposite direction. If the applied electric field is weak, the virtual particles will simply stretch slightly before snapping back together and disappearing. But if you ramp up the electric field strength to an ultimate critical value, known as the Schwinger limit, the electric force becomes so immense that it completely overcomes the binding energy of the vacuum. The field physically rips the virtual electron and positron apart, separating them by a distance greater than their quantum wavelengths. The virtual particles are instantly transformed into real, permanent, material particles of matter and antimatter. The electric field pumps its own electrical energy into the vacuum fluctuations, and that energy is instantly crystallized into mass, causing a fountain of real electrons and positrons to pour out of what appeared to be completely empty, dark space. The Schwinger limit represents the ultimate breaking point of the vacuum, the threshold where empty space can no longer hold itself together and begins to bleed matter. Currently, experimentalists are building next-generation ultra-intense laser systems, such as the extreme light infrastructure in Europe, to try and focus multi-petawatt laser beams onto a single microscopic point of empty space. By concentrating this immense amount of optical energy into a tiny volume, they hope to reach the Schwinger limit, popping matter out of the void in a controlled laboratory setting. When this experiment succeeds, it will be the ultimate demonstration that the line between matter and nothingness is completely arbitrary. The vacuum is simply a latent form of matter, an unignited fuel that can be coaxed into solid form if you strike it with enough electrical violence. This capacity of the vacuum to act as an unignited fuel has led theoretical physicists to ponder some of the deepest questions regarding the origin of our universe, including a concept known as the vacuum genesis. For generations, the biggest philosophical hurdle for the Big Bang Theory has been the question of what ignited the initial explosion. How do you get an entire universe packed with billions of galaxies out of absolute nothing? The framework of quantum field theory provides a logically consistent, mathematically rigorous answer. The universe did not begin from nothing. It began from a vacuum fluctuation. If we assume that before the Big Bang there was no matter, no stars, and no planets, there was still a state of pure space-time, populated by quantum fields operating in their vacuum states. This primordial void was subject to the same quantum uncertainties that govern our local atomic voids today. At some random moment, a massive, spontaneous quantum fluctuation occurred within that primordial vacuum. Due to the unique laws of inflation and general relativity, this fluctuation did not snap back and disappear. Instead, it triggered a local gravitational instability, causing that specific patch of space to undergo an explosive, exponential expansion. The vacuum energy of the field was stretched out, magnified, and subsequently dumped into the production of real particles, filling the expanding bubble with the hot, dense plasma of the Big Bang. This means that the entire cosmos is essentially a free lunch. The universe did not require a massive injection of external material stuff to be created. It required only a temporary, quantum rearrangement of a pre-existing vacuum state. The vast expanse of our night sky, the heavy elements forged inside stellar cores, and the very structure of our planet are simply the evolved debris of a single, ancient tremor that rippled through an eternal, underlying emptiness. The vacuum is the ultimate mother of reality, an infinite reservoir of potential that is fully capable of birthing entire universes out of its baseline fluctuations. To fully ground this mind-bending reality into our local human experience, we must look at how this active vacuum governs the field of chemistry and materials science, shaping the properties of the everyday objects we interact with. When you look at a diamond, it feels incredibly hard, rigid, and scratch-resistant. If you look at a piece of graphite inside a pencil, it feels soft, slippery, and easily rubs off onto paper. Yet both of these substances are made of the exact same chemical ingredient, carbon atoms. The reason a diamond is hard while graphite is soft is entirely due to the geometry of the empty space separating their carbon nuclei. In a diamond, the carbon atoms are arranged in a rigid, three-dimensional tetrahedral lattice. The electromagnetic fields filling the empty space between these atoms are locked into a highly symmetric, tightly bound configuration. When you try to scratch a diamond, you are not trying to deform solid material. You are trying to deform the intense, highly organized field structures that are woven into the void separating those carbon cores. In graphite, the carbon atoms are arranged in flat, two-dimensional sheets that are stacked on top of one another like sheets of paper. Within each individual sheet, the carbon atoms are tightly bound by strong electromagnetic fields. But the empty space separating the stacked sheets is populated by a much weaker field interaction, known as the van der Waals force. This force is a direct consequence of the spontaneous quantum fluctuations of the electron clouds within the sheets. The vacuum between the sheets is loosely coupled, allowing the layers of graphite to easily slide past one another when you press your pencil against a piece of paper. The macroscopic tactile properties of our world, whether an object is hard or soft, brittle or malleable, transparent or opaque, are completely dictated by the specific structural styling of the empty space between its atoms. The nucleus of an atom is just a passive weight, an anchor that pins the field lines in place. The true work of chemistry, the formation of bonds, the conduction of electricity, and the reflection of light, happens entirely within the active arena of the atomic void. The physical world is a sculpted landscape of forces, given form and texture by the specific ways that universal fields are channeled and constrained within the empty spaces of material matrices. This realization alters how we conceptualize the human body itself. When you look at your reflection in a mirror, you see a solid, continuous physical form. But as we have seen, if we zoom down to the atomic scale, your body is 99.999% empty space. The distance separating the nuclei of your atoms from their electrons is an immense, yawning chasm relative to their sizes. If you could somehow switch off the electromagnetic force fields that populate that internal void, the fields would collapse, and your body would instantly implode. The material stuff that makes up your physical form, the actual solid volume of your protons, neutrons, and electrons, is almost completely non-existent. You are, quite literally, an architectural scaffolding of fields, a pattern of energetic vibrations playing out across a universal vacuum. The boundaries of your body are not hard material edges. They are regions where the field intensities shift, creating a localized pocket of stable interactions that can move, breathe, and think. You are not a separate entity stranded in an empty world. You are a localized thickening of the cosmic vacuum, a place where the universal fields have woven themselves into a spectacular, self-aware knot. This insight provides a profound validation of our place within the grand hierarchy of nature. For centuries, the relentless march of scientific discovery seemed to diminish humanity's significance. Nicholas Copernicus showed us that Earth is not the center of the solar system. Edwin Hubble showed us that our galaxy is just one of billions of island universes scattered across a terrifyingly vast cosmos. And Charles Darwin showed us that we are deeply rooted in the biological tree of life. It was easy to look at this vast, empty universe and feel a deep sense of cosmic insignificance, to view ourselves as fragile, material anomalies clinging to a tiny rock, lost in a barren, sterile void. But the paradigm of quantum field theory completely corrects this existential narrative. It reveals that the void is not a sterile absence that isolates us. It is the very fabric that unites us. The space separating you from a distant star, or separating the atoms inside your hand, is a living, breathing entity. It is the ultimate ground of being, a continuous, all-pervading matrix that is constantly alive with the activity of universal fields. You cannot be separated from the universe because the fields that make up your body are the exact same fields that make up the entire cosmos. You are an intrinsic part of this cosmic fabric, a place where the vacuum has organized itself to experience its own existence. This holistic view of reality is beautifully summarized by the concept of quantum field vacuum alignment. When you move through the world, you are not cutting through an empty room like a ship cutting through water, leaving a wake behind you. Instead, you are a continuous wave moving through a permanent medium. As you walk across a room, the universal electron field does not move with you. The field stays exactly where it is, filling the entire room. What moves is the excitation pattern. The energy that defines your body is being transferred from one set of field coordinates to the next, like a wave rolling across the surface of the ocean. The water molecules in the ocean do not travel with the wave. They simply bob up and down, transferring their kinetic energy to their neighbors. Similarly, the points in the universal fields are simply bobbing up and down in response to your passage, shifting their energy configurations to manifest your physical form as you glide through space. You are a traveling symphony of field excitations, an eternal pattern of light and matter written onto the unmoving canvas of the universal void. As we look toward the final horizons of scientific exploration, this study of the vacuum remains the central arena where the next great intellectual breakthroughs will be forged. Every major frontier in modern physics, from the quest to build a theory of quantum gravity to the mystery of dark matter and the origin of the Big Bang, is fundamentally a quest to decode the hidden architecture of empty space. We are, like ancient cartographers, gradually mapping the coastlines of an invisible continent that surrounds us at every moment. To understand the full majesty of this scientific journey, it is helpful to look back at how far our concept of nothingness has evolved. We started thousands of years ago with the simple, intuitive idea that emptiness is just the absence of stuff, the space left behind when you take everything away. We watched this idea challenged by Aristotle, who declared that nature abhors a vacuum, arguing that a true void was a logical impossibility. We saw that dogma shattered in the 17th century by the bold experiments of Torricelli, Pascal, and von Guericke, who physically pumped the air out of chambers, revealing the invisible weight of our atmospheric ocean and establishing the reality of a material vacuum. Then, we witnessed the profound conceptual shift of the 19th and 20th centuries, where Faraday, Maxwell, and Einstein populated that mechanical vacancy with the invisible structures of fields, proving that light and gravity could travel through the void because they were intrinsic ripples in the geometry of space itself. Finally, we experienced the radical double revolution of quantum mechanics and quantum field theory, which revealed that fields can never be truly still. The uncertainty principle condemns the vacuum to a perpetual, restless hum of zero-point energy, vacuum polarization, and virtual particle creations. We discovered that the vast, seemingly empty spaces inside our atoms are actually highly active junctions where universal fields overlap and interact. We learned that 99% of the mass in our body is not found in solid material, but is the raw kinetic energy of fields churning within the empty spaces of our atomic nuclei. We learned that we are swimming through a pervasive Higgs field molasses that slows us down and gives us weight, and that the ultimate fate of our universe is currently being driven by the dark energy hidden within the vacuum's expanding pressure. We looked at the edge of black holes, where Hawking radiation proves that the vacuum can steal mass from gravity to birth real particles into the cosmos. We looked at the dawn of time, where cosmic inflation stretched the subatomic jitters of the vacuum across light years of space, freezing them into the grand architectural blueprint that guided the formation of every galaxy, star, and planet in existence. We witnessed the vacuum acting as an optical lens through birefringence, and we looked at the ultimate breaking point of space through the Schwinger effect, where pure electrical force can rip matter directly out of the dark void. This is the strangest, most beautiful truth in all of human discovery. Empty space is not empty. It is a crowded, dynamic, and vital reality. It is the canvas, the actor, the force, and the substance all at once. The next time you look at the seemingly vacant spaces around you, let the illusion of emptiness fall away. See the invisible webs of the electromagnetic field vibrating with potential. Feel the gentle drag of the Higgs field giving mass to your form. Hear the silent, subatomic hum of the zero-point fluctuations jittering at every point in the room. The void is not nothingness. It is the fullness of being, an eternal, restless ocean of energy from which our entire world has condensed, and into which it will eventually return. Once you understand what the fields are and what they do, you will never look at empty space, at matter, or at reality itself the same way again.